Now, one issue we had with Rutherford's reaction, with his experiment, is one that we didn't talk about earlier, but it's charge. So that helium nucleus and the nucleus of the nitrogen atom, those are both positively charged. And because they're positively charged, that means as they get closer and closer, there's going to be a force, a coulombic repulsion force, that's going to try to push them away. Because of that means I have to be going very, very fast to have this reaction happen. I have to overcome that coulombic repulsion force to actually have them collide and the reaction to take place. And if it's going very fast, it means it takes a lot of energy. So it'd be nice if we could cut down the required energy. Like, I don't want to have to spend so much energy getting this particle to insane speeds just to have the reaction happen. So why don't we use a particle that doesn't have a charge? So for many nuclear reactions, we'll use a neutron to start them, especially when it comes to fission. Why a neutron? Because a neutron has no charge. And that means there is no repulsion force for a neutron. Okay, so time for some alchemy. What we're going to do is we're going to see what happens if we bombard Mercury with some neutrons. So we have Mercury right there. And guess what? It turns into gold. This is just one of the possible reactions. So neutron comes in, smacks into the Mercury, and what happens is it leaves and it steals a little bit of charge. So one of the neutrons in my Mercury becomes a proton. Make sure I say this right. Sorry, when my protons becomes a neutron, I said it completely wrong, and my neutron becomes a proton. You could also say that the neutron smacked a proton out, but that's beside the point. So we'll have the same charge at the beginning, same charge at the end. And let's check to see if this all works out. So we can write it in our earlier form. So neutron, notice it has a 0. That means it has no charge. Has 1 nucleon because it is 1 nucleon. Hits Mercury, 198 nucleons, charge of 80. And when it leaves, I now have 198 nucleons still here, but now it's got a charge of 79 because my neutron stole some charge from one of the protons and became a proton, or it knocked a proton out. There's lots of ways you can think about that. The exact process that happens to get a proton out isn't super important for us. Okay, now we can check our conservation equations. Now this is really simple to do because it's literally just add everything on top, everything on the bottom, and see if it matches on both sides. So first off, conservation of nucleons. I have 1 plus 198, which is equal to 198 plus 1. So both are 199. It matches. Really simple. Conservation of charge, 0 plus 80 is equal to 79 plus 1. 80 is equal to 80. So this checks out. This is a possible reaction. Now, the question here is, why was it this reaction? It could have been others. Like, for example, I could have had the neutron smack into Mercury and just stick. So Mercury has 1 more nucleon, and it gives off a gamma ray to get rid of any excess kinetic energy. Well, as for the why of that, that's going to go well beyond the realm of this course, but there's a lot of cross-sections which will say which one is most likely to happen, which of these reactions is most likely to happen for a particular collision. And so we'll use that in the future to determine which one's most likely to happen. Okay, before we head out here, let's talk about one last thing, which is the compound nucleus. So for all of these things, it doesn't always happen, but it can, where the two particles will not just bounce off of each other, but they will, for a brief period of time, become a compound nucleus. This is an intermediate nucleus, which is simply saying I have both of them, they stuck together, and the star is saying that it is unstable, because it has all of that extra energy in there from the kinetic energy of the particles. Because it's unstable, it's going to typically decay and break apart. So that extra kinetic energy, that's called excitation energy. And it can do lots of interesting things, but somehow this particle has to get rid of it, otherwise it can't stay that way. So for us, we're going to say it breaks apart, but also sometimes it will just emit the energy as a ray, as a gamma ray. And this compound nucleus, it lasts on a very, very short time scale. So 10 to the negative 14 seconds, that's 10 femtoseconds. That's ridiculously short. So this happens almost instantaneously. So with this, we've seen how we can look at different reactions. we've seen how we have a better projectile in a neutron. And we're going to be using that projectile to help ourselves understand how we can develop reaction rates and how we can develop the likelihood of a particular process happening in the future. So thanks for watching. I'll see you all soon. Bye-bye.